Okay, we're going to review the work of Dr. Thierry Paul on noncommutative nonlocality in quantum physics. And I had seen his name before in various papers, but for some reason I searched hiatus and noncommutativity, and it came up with this paper of his called Species of Spaces, and it's focused on noncommutativity. He came out, I think, originally in 2012, and then it was reissued in 2021. And so he has this quote in the beginning: "I feel confused cracks, hiatuses, points of friction." And he's quoting this avant-garde play, and it turns out he's not afraid to have a broader sort of Renaissance approach to science, and he has several papers on music that he references. So that was exciting to see, because he's making the connection between noncommutativity and music, and so he corroborates the same emphasis that Alain Kahn has made as the truth of music and the truth of reality in quantum physics. So when I was looking up hiatus, I was just interested about the definition of hiatus as a space between vowels, Vienna. So when you say that word, there's a slight gap or space between the two vowel sounds, naive, and that gap can be marked with the umlaut. It's not quite the same meaning as umlaut, but it's to differentiate the two vowels, so cooperate, and you put that diacritical mark above the second vowel. And it's considered archaic now to use that to differentiate the two vowels, the gap between the two vowels. So I found that pretty interesting, because vowels, they resonate, they're used in mantras, and so they're closer to music in phonetic language. But then when you have the two gaps between them, it kind of emphasizes that resonance of the overtones and undertones. And so that gets us into this paper of Paul, or Thierry Paul, Dr. Thierry Paul. His big point is that in noncommutative quantum algebra, there is no geometrical object or manifold that describes the space. So you're using a phase space that he says is actually just basically time and frequency. That's nonlocal. So that corroborates what I've been saying. He refers to the same study that Alain Kahn refers to, how you cannot visualize the shape of a drum because of this. The drum can be the same frequency, but it can be two different shapes that have the same frequency. So it can be isospectral, meaning the same frequency, but it's not isomorphic, meaning it's two different shapes. And that's because it's non-commutative. So that's the big point that Alain Kahn also makes. And so then I happened upon him giving a talk as part of a military-funded conference at my alma mater, University of Minnesota, mathematical physics conference. So he makes the same emphasis as Basil J. Haley, that because in quantum physics you cannot have the Planck constant tend to zero, therefore quantum physics is the foundation of reality instead of the other way around. And that's the big problem today in quantum field theory, is they're trying to impose relativity onto, or impose quantum physics onto classical physics, and not the other way around. So I'm glad that he's making that same point that Basil J. Haley makes. And so here's Thierry Paul, Dr. Thierry Paul, giving a talk. He's got several talks on YouTube, and so he's saying that if you try to make h bar Planck's constant over 2 go to 0 as a classical limit, this rule fails, and so the classical underlying space is not the standard one, and it must be a noncommutative structure to be a true quantum phase space. And so that's why h bar has to be greater than 0. And so that noncommutative structure is what's below the uncertainty limit of quantum physics. So he understands that. So he's right on the same page as Basil J. Haley. In fact, he has a paper about Bohmian physics, but I didn't read it in detail. He's got a lot of papers, and in fact he won this award. I just watched him receiving this award, and he was really honored to get the award. He got kind of emotional about it, which is good, because these are his colleagues recognizing his work. The Tullio Levi, I'm gonna just hack that word up, so Kavita Award Prize. And then he mentions, well, it's a good thing he got this prize because everybody uses. I've seen the name before, obviously. I just didn't know how to pronounce it, but it's basically a way to organize the quaternion numbers as matrices, and so you have the depth of 0, 1, and -1 in three-dimensional space, and it's non-commutative. So this immediately reminded me of the music theory ratios of 2, 3, and 3/2, because it's non-commutative, and how that relates to 1 and -1. So in other words, in terms of matrices, you have 0, 1, and -1, and the value of the time changes the number. So this is foundational to quantum physics for the using time as an operator as this non-commutative phase space, and this is the emphasis of his work, as well as Basil J. Haley and Alon Khan. So if I equals j, it's 0. If it's ij, then it's -1. -1 if ij equals 2, 1. positive 1 if ij equals 1, 2. Okay. So I'm not going to go into all those details because that's not what I'm focusing on here. But okay, so yeah, it's based on this permutation of these dimensions. Okay, so anyway, this is species of species. If we search non-commutative in this, we get 63 results. I don't know who Alex is. Alex Views. Alex's deep influence on me. Anyway, so I'll just go through this real quick. Yeah, so he gets into the non-commutative torus and frequency, and so it's very, very much based on Alain Kahn, which he says that's true. Perfectly in accordance with the philosophy of non-commutative geometry of Alain Kahn and the birth of the efficiency of the quantum paradigm, which gives a stable feeling provided by the macroscopic world. So non-commutative structure, one has to put on the sphere, right? So that's the block sphere. Then it gets into the set of frequencies, the eigenvalues. Okay, so I like how he says there's no need to recover the classical space. There's very much emphasizing the non-commutative truth of reality. So the other thing he gets into is the time infinity. Because of this non-commutativity, you have a negative infinity of time along with a positive infinity of time. And that's where you get into the problem of why it can't just be turned into a classical physics. Here we go, the time arrow. Negative diverging times. So this gets into the noncommutative tori, which I don't even think he's got an image of it. And the frequencies. What replaces this concept of frequency, which doesn't exist in classical mechanics, is the noncommutative algebra. Oh, I like how he uses that term classical frequency to differentiate it from noncommutative. I'm going to start using that. Okay. Cool. So he's emphasizing that the frequencies are discrete in the quantum spectra, and they're discrete and they're non-commutative, and this is also the truth of music, as he goes into. So it's a big temptation to consider the non-commutative frequencies and time as a foliated leaf, and to consider the non-commutative algebra to be associated to this very singular object. So he's pointing out that this is not true, that you can connect the two, but they're not equivalent, that you have to have this process that cannot be visualized as a manifold. So that's a great point. It's good to see that he's emphasizing that. That's the same truth in non-Western philosophy. So that's why he doesn't have an image of the non-commutative torus. The frequency spectrum, though being fully discrete, tries to mimic, as h bar goes to 0, a continuous one. And so he's saying this creates what ends up being a chaotic physics in the classical realm, which is pretty fascinating. Okay, so I'm almost done. Classical limit is as stable as quantum mechanics at the condition of letting it live on the right structures, different from the ones of the underlying classical dynamics, and keeping track of some residual non-commutativity. This limit, quote, space is not an absolute one, as the one of Newton and Kant. It depends intrinsically of the dynamics itself. The dynamics come before the space. So he's definitely got a lot of philosophy of science in here. So he's emphasizing frequencies instead of eigenvalues. And he's just saying that that also explains the Pauli exclusion principle as the stability of matter from the 1/2 spin. A major achievement in quantum physics considers the understanding of statistics of, well, a trace of chaotic behavior. Our approach links directly frequencies to the geometry. Yeah, so that's the connection again back to music theory. So this is a really cool paper. Okay. So now, yeah, because I was basically saying it was chaotic math in my master's thesis, so I'm glad that I wasn't totally wrong. Okay, so, anyway, there we go. He's got the Alon-Khan sources, 1985, 1994, so he's gone all the way back. And then he's got an earlier paper of his on noncommutative, 2011. Okay, so now we're going back. He gives this non-technical talk, which is a lot of fun. He takes his time, he's not trying to make anything complicated, but he wants to explain quantum physics. So he's basically like, you got two parts of quantum physics that create this quantum measurement problem. You have the evolution of the wave function, the Schrodinger wave function as a classical, as a partial differential calculus that's based on causality, and then the second part is when you do the actual measurement, and so you get a unpredictable result that's and nevertheless very precise because it's an expectation value, so you can reduce the probabilities to the 10th decimal point. So he's saying that you need to forget about the continuum space that you have in Newton. This is you have discrete things because you have a vectorial space, and it's a two-dimensional vectorial space. That's what you start out with. So this is what Basil J. Hiley also emphasizes, that you basically have time and frequency as the foundation. He doesn't go into that in this non-technical talk. He's just going into the paradoxes that he said. He's like, in quantum physics there are no paradoxes, but you have to rely on the mathematics directly. So when you talk about it, then it appears paradoxical. And then he used the analogy of 3D glasses in the movie theater. And he's like, you got to use both your eyes and then put on the 3D glasses, And anyway, so it's a fun talk. He makes a couple jokes. And the non-commutativity is the we already went over that. And so the density operators in noncommutativity replace the probability measures. This is actually a different paper that's citing the Alon Kahn 1992. Okay. So, so he's comparing this as mathematics versus music and mathematics versus quantum mechanics. And that's where he gets into the musical drum. This is another one of his talks. And so anyway, okay. So this brings us to the music part, which of course is my focus, is on the secret truth of music being noncommutativity. So he makes some really cool points about this. He's got a paper from 2020 on mathematics and music. And then he gives another YouTube talk, which I didn't link, but I think I can't remember which talk it is now, but I think it's the one up here. I'm sure it's one of these links, but he basically says, this reminds me of musical notation where you get something extremely powerful from redundancy. So again, that's exactly what Alon Kahn calls 2, 3, and infinity. So you have that redundancy as an invariance of the noncommutativity. And then he says that the invariance of time gets broken because of the negative infinity time. So you have to go to an unstable manifold. By unstable, he means the non-commutative that you cannot visualize, as he says up here. So like here you have a manifold for commutative algebra, but for non-commutativity, no manifold. There is no manifold. So in terms of music, that means you're relying on listening. And then he says, our ears, since you have this quantum correction. So he's talking about when you're listening to the piano. He says if you listen to like the lowest note on the piano, you can then switch to figure out the precise frequency. In other words, you're able to localize the pitch in space based on the low frequency gives you a better precision of the geometry of the pitch. And that this is the same thing as that non-commutative unstable manifold that's delocalized. It's a delocalized process, that listening process. So he directly makes this connection that Alon Kahn makes, that it's that listening to music. He says it's like when you listen to the lowest note on the piano, and then you can recognize what pitch it is. And so flow at infinite time escapes from the classical paradigm because it does not preserve the geometrical structure of points in space. After infinite evolution, single points would become extended objects. So this is where you can turn it into a chaos mathematics for classical physics. And then he says that the quantum frequencies of the system become the flow of the classical. The link is subtle. So you have this invariant of the quantum flow, that namely the frequency. So that's the invariance of the noncommutative frequencies. And it's a natural quantum object because it's discrete. That's again meaning it's nonlocal and noncommutative as this double quotient. And that replaces the concept of classical frequency, which doesn't exist in classical mechanics. And it's not an integrable system. So you can only use this non-commutative algebra and not no point particle. And so that's again exactly what the point that the emphasis of Basil J. Hiley and Alon Khan. So I was very happy to see him make these two big points about music, and then to have that connect back to the basis of his prize, which is this invariance of the non-commutativity, as this what Alon Khan calls 2-3 infinity, which is basically like your double quotients of exponentials and square roots as a discrete frequency in time, non-locality. And of course, I don't do the mathematics. I don't actually do any of these calculations, but Alon Khan, he converts it to the frequencies of the photons from Heisenberg. So it's nice to discover another scientist who understands quantum physics on this deep level of the non-commutative, non-local time as negative infinite time. And of course, that is the secret of meditation as well, through this listening process. He gets into biology too. He doesn't get into non-commutative quantum biology, but he's basically like, you have to decide what's making the measurement, and whatever the measuring instrument is, that's where you have to be. That's your classical limit of the quantum. And it's a good point. Well, thanks to Thierry Paul, Dr. Thierry Paul. Very cool research. I mean, he's got a ton of papers, obviously, that I could study him. I could probably try to learn from him. But here's another one of his non-commutative papers. Let's see what this one says. Nowadays, the quite popular notions of quantum groups have no underlying group or geometry type objects. Okay. So yeah, this is all about the same point, is that again, there is no underlying object for noncommutative non-locality, and that's what Westerners have such a difficult problem with. And you have to get rid of Newtonian continuum physics, which of course is what everybody learns in high school. So most professional physicists, they can't handle this because non-commutative manifold is a non-commutative algebra. And so then it gets into the Mobius strip and the torus. And yeah, he gets into a lot of interesting philosophy of science. So this is basically the Dirac dance. The straight line arrives to the right side. It has to be continued by starting again on the left side. So that's that inherent flip. Totally unreachable. So you can't have any kind of image to represent it. It would have to be a black drawing, the emptiness. So let's see what else we can glean. He gets in the partial differentials. Of course, Basel-Haley's big point is you need to have a two different derivatives, a forward and backwards derivative. But that's just to try to convert it to classical physics. Let's see. Yeah. So this is a cool paper because he's trying to, like, people who don't really know a lot, he's trying to explain it, so it's good for me. No underlying object to this new entity, because it's a second degree equation. And that's Basil J. Haley's big point. So it's a process. So this is the quantum side over here. So it's not like a partial differential equation. Nothing like a space. Non-commutative algebra. Nothing like a manifold. Nothing like partial differential equation. So you have operators, not functions. Noncommutative. Entities without objects is the paradox. So this is the same paradox of what Basil J. Haley calls pheronomy, because you have motion without any cause to the motion. So there's no matter causing the motion. It's just time and frequency. So now he's trying to connect it back to classical physics as chaos. The noncommutative space is a space by the fact that topology can be defined on it. And then he makes a connection to music. The reader, let's see, so that's right here. Exporting this outside mathematics in real life, so to speak, would constitute a fantastic issue. He's quoting, I don't know who he's quoting here. These are his other papers where he writes about music. Okay. The noncommutative manifold only exists in its noncommutative algebra. Okay. This is he's quoting an essay on Beethoven. That's interesting. Anyway, so that just proves again, he's making the connection to music. So, that's what I already quoted. So I just wanted to make sure I gave him enough consideration, because he's got several articles on music, but they're in French, so, and it's like he's talking more about classical music. He talks about Stockhausen and Chopin and Beethoven and okay, there we go.